Okay, so welcome everyone to CS 11747. This is Neural Networks for NLP. If you thought you were in fundamentals for microeconomics, that's not here. So hopefully this is the right class for you. So this is a class about neural network models for natural language processing. I'm assuming that the people here are interested in natural language processing and ideally have taken a class on natural language processing. We have the prerequisites being algorithms for NLP. That's not absolutely required, but I will be expecting that you have at least some background here. And the goal of this class is to give you the fundamentals to understand most cutting-edge research in natural language processing that uses neural networks. So you should be able to pick up a state-of-the-art paper, understand it, have an idea at least of how you would implement it, and maybe do research on the topic or implement state-of-the-art cutting-edge systems based on that. That being said, I'm going to start from the basics very quickly. I'm going to go through the basics very quickly. And then after we go through the basics, we'll start getting into deeper details. So if you don't have much experience in NLP or don't have much experience in neural nets, at the very beginning, I'm going to ask people to catch up, go to TA office hours often, try out the example code on your own, etc. So that being said, I'd like to start out. So my initial premise here is that we all want to handle language with computers in some way. And one of the interesting things about language is that it's very difficult, very complicated, and hard to handle with computers. And to give an example of this, I'm going to try something called acceptability judgments. How many people does that sound familiar to? How many people have taken like a linguistics class at some point? So this is a very common thing in linguistics, which basically says, do you think these sentences are grammatical or natural sentences in a particular language? So the first one, who thinks this is okay in English? Okay, that's most people. If you already aren't raising your hand at this class, at this point in the class, then raise your energy level. I'm going to have to be at full energy this entire time, so I hope everybody else will. What about this one? Okay, good. Well, nobody raised their hand for that one, so I think we're all set. Oops, sorry. I gave you two for the price of one there, but what about these ones? No? So what's wrong with the first one? Jane went to store. It's missing a preposition. What else? It's missing an article, yeah. So it's missing some of the important function words. What about the one after that? Morphology, conjugation, yeah. So it's you're conjugating incorrectly. So you're taking the irregular verb go, and you're translating it like a regular verb, go, right? Yeah.
So quick question, the third sentence might be okay in some languages?
Yes. I'm actually going to talk about it. What language were you thinking of?
Like I'm from China, so Chinese.
Chinese, yeah, exactly. So, Chinese doesn't have articles, for example. So, well, mostly doesn't have articles. Japanese almost entirely doesn't have articles. So yeah, this is a very language dependent thing. What about this one? The subject and the object are reversed. What's?
If we think of the store as an entity,
Uh-huh.
then Jane kind of inherited it, so the store went to Jane.
The store went to Jane. I love this part because every single time somebody comes up with a way to rationalize this sentence, and every single time the rationalization is different. So that was a good point. So you mean like Jane inherited the store. So the house went to Bob, the store went to Jane. So yeah, that is correct. But in the most normal interpretation of this, stores are inanimate objects, and inanimate objects don't tend to go places. And then what about this one? Yes. Oh, yeah, you were raising your hand to say yes, this is okay. So, yeah, so semantically, a food truck it's not an animate object, but it's a movable object. And in a way, it's kind of a store, right? So, there are certain stores, there's other interpretations of this where it could be okay, but it does feel a little bit unnatural if you say the store went to somebody. So, the first one's okay. The second three are syntactically incorrect. The fourth one is maybe semantically incorrect. So if we thought about a way where we were a linguist and we didn't know machine learning at all, which might not be the case for a lot of linguists these days, but let's say we were a linguist who didn't know machine learning, you could come up with rules. And these rules would look maybe a little bit something like this. Create a grammar of the language. So you come up with some grammar of the language with grammar rules and say, well, before a non-plural noun, you need an article most of the time, unless it's a river or something like that, and then, or a noun, expressing an action or something. You also need to consider morphology or conjugation, and you also need to consider its exceptions. Oops. You need to consider semantic categories and preferences. So you need to know that it tends to be a dog barking and a cat meowing, and stores or other non-movable things tend to not move, right? And also that going is a type of moving. But there's also exceptions. So, birds tend to fly, but penguins tend to not fly. So this is complicated. And then, as we said, in some languages in the world, the rules differ, right? So I speak Japanese, so I can come up with these. Can anyone else do the acceptability judgments on the Japanese sentences in here? There's usually one or two people. If I said Chinese, I think I'd have a lot more hands. And if I said Hindi, I'd probably also have a lot more hands. But yeah, so I can do the same acceptability judgments. These are basically translations of the previous sentence into Japanese with grammar errors and all. Yeah. So we have these phenomena to handle, which are morphology, syntax, semantics, world knowledge, discourse, pragmatics, multilinguality. And especially if you consider all of the previous ones corresponding to the last one, that's a lot of rules that you need to be writing, and they're super complicated, right? So that's the reason why NLP is hard, and NLP is still not solved yet. So neural nets, the name of this course is Neural Nets for Natural Language Processing. And the two functional words here are neural nets and for natural language processing. And from the point of view of neural nets for natural language processing, I'm going to view them more as a tool to do the kind of solve the kind of linguistic problems that we have, the problems that we encounter when trying to build language systems. I'm not necessarily going to view them as something where we're trying to come up with better machine learning algorithms, except from the point of view of solving problems with respect to language. But that being said, there's lots of problems that come up in language that don't come up as readily in other places. So it's going to give us a lot of interesting techniques that you might not get in your standard deep learning class. So this class will give you the tools to handle the problems, and as I said, it's a graduate class, and it's going to be largely focused towards building, state-of-the-art models, state-of-the-art systems, given the current techniques. Are there any questions so far? Maybe it's straightforward. Okay, cool. So next I will go to the class format and structure. So the class format. Before the class, I ask people to read a brief overview of material on the topic. The reason why I do this is because I want everybody to be kind of on the same page before we come to class so we can go deep into particular topics. These readings will usually be maybe anywhere between 6 to 12 pages. during the class, at the very beginning, we will have the quiz. This will be simple questions about the required reading. They should be relatively easy. They will be given on Canvas, so please sign up for the Canvas class here. The first couple times we'll be bringing paper quizzes for people who have trouble signing in or something like that, but we like to largely do it through Canvas. The quizzes need to be taken in person, and we'll put a thing on the board with the quiz number here. So you shouldn't be sharing that with people who are not in the class, for example. If you are gone for whatever reason, if it's sickness or official travel or stuff like that, you can get the quiz excused. There will be summary and questions and elaboration. So we will summarize the material, field questions, and most importantly, elaborate on the details and talk about advanced topics, important things that you should be knowing. And in some cases, not all cases, we might have a code walk or some sort of looking at data or something like this to make the ideas more concrete and try to bring up other questions. After class, if there's a code walk available there, I highly recommend that you download the code, look at it, run it, try it out yourself. We don't have a huge number of assignments in this class, which is kind of intentional. Each of the assignments is larger though, and they get harder quickly. So this also relies on you kind of, studying on your own, not entirely based on the assignments, especially if you don't have a lot of experience in the area already. And fortunately, let me skip this part for a second. Fortunately, we have lots of wonderful co-instructors and TAs for this class. And all of us hold office hours once a week. There's at least one every day. So if you have any questions, please feel free to stop by. So I'm the instructor. I'm Graham Neubig, assistant professor in LTI. And the co-instructor is Peng Fei. Peng Fei, if you could stand up. So Peng Fei is a postdoc in LTI, and he has lots of experience with like multitask learning, interpretation models, methods, any other.
Yeah, and there is something I focus on some tasks such as the summarization and the tagging.
Yeah, summarization, also like a little bit of information extraction related stuff, right? Yeah. So you might forget these things, but keep in mind, like all of the TAs have experience in a lot of different areas. So if you are interested in something, please ask. There's still seats if you want to sit down. So. Then the TAs are Aditi. So if you could stand up one at a time while I call your name. So Aditi works a lot on multilingual learning, morphology, and stuff like this, named entity recognition. Chunting kind of overall does like machine learning models for NLP, but latent variable models. Also has done a lot of multilingual stuff as well. Hiro, in the back over there, has done text generation related stuff and like also working with knowledge bases. Pengcheng has done semantic parsing, so parsing to like executable meaning representations and also QA related things. So if you're interested in QA, he'd be a good person to ask. Vidisha in the back. I know you're doing summarization now, but do you have any other things? Yeah, so summarization, generation, knowledge-based reasoning. And Z has done a lot of work on MT and meta-learning related stuff. So if you forget all of these things, which is pretty reasonable unless you're taking notes, feel free to look at the web pages of people and see who would be good. And we'll also try to assign TAs based on like interest match with the projects you're going to do. So going back, scope of teaching. So I kind of covered this a little bit already, but in terms of basics of general neural network knowledge, I'm going to cover this very briefly. The reason why I'm going to cover this briefly is there's lots of classes on neural networks in CMU or other places, and I think a lot of people will have taken this already. If you don't have a class, if you haven't taken a class on neural networks or haven't built neural networks before, I'd highly recommend that at the very beginning of the class you read through the reading. It's a lot of content, but it's good and will get you kind of up to pace. And also try out the code examples, run them, download them, run them, etc. And I think this will help get you at least the basics that you need. We'll also have a recitation on implementing a language model in PyTorch, I guess. And Pengcheng will be doing that. We'll have an announcement for that later. In terms of advanced training techniques for neural networks, we're going to talk about this a little bit, but mainly with respect to things that are relevant for NLP. Advanced NLP-related neural network architectures or training techniques, these will be covered in, neural network architectures, these will be covered in detail, because that's kind of one of the main things of this class. And also structured prediction and structured models in neural nets. So how do you predict complex outputs? How do you encode tree structures or graph structures, or how do you predict tree structures or graph structures? This will be covered in detail. And also, because one of the goals of this is that people can actually build things with neural networks for NLP tasks, we're also going to cover a lot of kind of implementation details, like how do you make things fast? How do you debug when things are not working well? How do you interpret your model outputs? In terms of assignments, the course is largely group assignment based. So after the first assignment will be individual, all the following ones will be group based. And the group will be 2 to 3 people. If you don't know anybody in the class, don't worry, we will have a matching process. You can pick your own groups, but we'll also match people who haven't found a group yet. So assignment 1 is a text classifier. So we need to implement something that does text classification. This will be done individually, and we'll also ask people to fill in a questionnaire about the project topics they're interested in. And this is for matching if you haven't found a group by then. Assignment 2 we'll ask you to basically have picked an interesting looking project topic and do a survey of the state of the art with respect to that topic. For assignment 3, we will ask you to implement a paper in an NLP conference basically from scratch. You know, you can use a neural network library like PyTorch or something, but you can't just download the code and run it. And we'll ask you to reproduce the results of a state-of-the-art model. So I've taught this class. I think this is my 4th time teaching this class. When I first started teaching this was really easy. Now it's really hard. So what we're going to do this time, we had some people last time who had trouble doing this because they picked like Googletron trained on 50,000 TPUs for 7 weeks or something like this. And there's no way you're going to be able to do this with the $150 of AWS credits that I'm going to be giving you for the entire course. So we're going to recommend some papers that we think are a manageable implementation burden. But if you want to try something else, just contact us early and we can look at it and say, yeah, we think this is reasonable, or no, you don't want to be training this because it will take your entire lifetime. So. Then the final project is to perform a unique project that either improves on the state of the art or applies neural models to a new unique task. And when I say improve on the state of the art, I mean taking what you did in section 3 and making it more accurate, making it faster, maybe making it more interpretable if you can convince me what more interpretable means, for example. So. But everything will have to be quantifiable. So you need to have some like metric of your success and say, if I improve this number, I will have succeeded at this project. So for things that are a little bit more open-ended, we'll have to discuss that more, and we can discuss that in office hours, for example. So yeah, this is kind of it for the class structure overview. Are there any questions about this now? Yeah.
Would you be providing a list of topics we would choose from?
Yeah, we will be providing a list of topics, but not for a week or two. Maybe shortly before assignment 1 is due, and assignment 1's due early February, I think. So, any other questions? Yes.
Would we use it for our teams?
So you will need to submit assignment 2 as a team, and that's due around the end of February. It's written on the website. I don't want to make a mistake, but it's due around the end of February. And when you turn in assignment 1, you'll fill out a questionnaire, and if you don't have a team yet, we'll look at the topics and we'll match all the. We won't require you to work with that person, but we'll give a suggestion and say, hey, you can meet up and talk. And I think that's about 80% successful. Like 80% of the time, people form a team. You know, other times we have to find another. Good question. Any others? Okay. So yeah, feel free to interrupt with questions anytime. Yeah, I'll be happy to answer. Okay, so neural networks, from my point of view as somebody who's interested in language and building systems that work well in language, I view them as a tool to do hard things. So to give a very simple example of this, an example prediction problem is sentence classification. And sentence classification, to give a very simple example, simple in terms of like intuitive, not simple in terms of actually solving the problem well, is sentence classification. For example, if we have I hate this movie and I love this movie, we have 5 classes where each of these classes is very good, good, neutral, bad, very bad. So this first example, what do you think the first one is? Very bad. Okay, yeah, I think that's pretty straightforward. What about this one? Very good. Okay. So that's good. You have at least the accuracy of a bag of words classifiers. So, so how do we form a classifier that tries to solve this problem? So the very simplest way is using a bag of words classifier. I'm going to express a bag of words classifier maybe a little bit differently than you normally do, and that's to make connections towards a neural network classifier later. So if we have our first try bag of words, basically what we do is we take word I here, and we look up a vector of continuous values of size 5. So each of these values is equal to the labels that we have in the output. So we had 5 labels, 5 values. And we do this for all of the other words in the input. We also have a bias term. So the bias term is, just corresponds to how likely each of the labels is. So if very good and very bad are very common, like on Amazon, 5s are most common, 4s are second most common, 1s are third most common, and then 3s and 2s. So then the bias form term would have the highest score for 5, etc. We then add all of these together and get a set of scores here. We can then take a softmax. I think most people here know this. If you don't know this, it basically turns real valued scores into a probability distribution that sums to 1. We'll talk about it exactly later. And this can give us probabilities of each of the outputs. So this actually, for some text classification problems like topic classification, this works relatively well. If it's a sentence about tennis, then if the word tennis appears, you're pretty likely to have it be about tennis. If the word tennis appears and the word Federer appears, then you're much more likely to have it be about tennis, right? So if we think about this, what do our vectors here represent? Each word has its own 5 elements corresponding to one of the output labels, where if the word is a high sentiment word, it will have a higher score for very good and good. If it's a low sentiment word, it will have a score for bad and very bad. So yes, there's an example. So, you know, this will work for our really, really simple examples. But then what happens when we get something like this, right? I don't love this movie. So what is the class for I don't love this movie?
It's probably good. It should be bad, but it would probably be, because you have to be able to understand that negation. The bad word model might not be able to.
Oh, okay. So what is a human? What do you think the class label is? Bad. I'd say maybe it's bad. It's maybe not all the way to very bad, but let's say bad. There's that. Now, what about there is nothing I don't love about this movie? Very good. That's like better than I love this movie, right? You know, it's like about the highest possible praise that you have, right? But if you look at the actual words that are included here, you have love. And then if you have I don't hate this movie, for example, it varies by one word. Maybe it is neutral. I don't know. It's not praise, but it's also not, you know, horrible. So if you do something like this, just adding the vectors won't work because, you know, love is positive, hate is negative. So if you just switch out one, then obviously I don't hate this movie is going to be worse than I don't love this movie. And then, you know, you go even farther, there's nothing I don't love about this movie, and it's just kind of confusing for a bag of words. So what we need are combination features. So for example, to give a very simple example of a combination feature, this isn't the greatest combination feature, but what if the sentence doesn't include, we don't look at whether the sentence includes love, but we look at whether it includes don't and love at the same time. Unfortunately, a bag of words model cannot take this into account, right? Because it's looking at all of them independently. And then if we say, there's nothing I don't love about this movie, you would need something like nothing I don't in love. And then, you know, that would correspond to don't, I, love, and nothing all appearing at the same time, right? So the basic idea of neural networks is that basically what we want to do is we want to you know, look up some sort of representation of all of the words in the input, and then we want to take some function. Before I was using the bag of words function, but instead of using the bag of words function, we want a much more complicated function that can extract the appropriate combination features that allow us to solve the task that we want to solve. And once we get those features, we then take these features, turn them into scores, turn them into probabilities, and use them to make our predictions. And actually, a thing I should mention while we are at it is this is also linked from the website, but we have these code examples where the code examples look like this, and this time we have intro in intro PyTorch. So historically, I implemented the code for this in Dynet, which is a neural network toolkit that we made here at CMU. Now we also have examples in PyTorch. So intro is intro Dynet, intro PyTorch is you know, intro PyTorch. So you can click on either of these, and they will have basically an example of how you can implement this bag of words in an IPython notebook, for example. So we have a bunch of things that like turn words into integer IDs, look up outputs, etc. And then here we have a place where we can calculate scores using the bag of words model. So this will essentially take the sum of all of the vectors that I had looked up in the slides. So if you want to go and take a look at the code, This code is all available on the site, and you can download. And all of it also comes with data. So we have data, and this is the data for this particular thing. And if you look at the dev set, it basically comes with labels where label number 3 is good, label number 4 is very good, 2 is neutral, etc. So you can actually go and run the code yourself if you want to as well. So yeah, if we can look at this, you know, we have a warm, funny, engaging film is marked as very good, and we have here's yet another studio horror franchise mucking up its storyline with glitches casual fans could correct in their sleep. So that's pretty harsh, let's say. Yeah, you can use this data to play around with things as well. And all of the models that I'm going to talk about here, including this continuous bag of words model, which I'm going to talk about next, are implemented there for you to try out. Okay, are there any questions so far? Okay, so next I'm going to talk about the continuous bag of words. And what the continuous bag of words is it's basically a bag of words model. But instead of looking up the scores directly, we instead look up some other vectors, where these other vectors are not scores. Rather, these are embeddings, where the embeddings are kind of an arbitrary continuous valued vector that corresponds to this word. And you know, I think a lot of people have heard of this, you know, embeddings from word to vec, fast text, whatever, or the word embedding, they could just be randomly initialized and trained with the model. So what the continuous bag of words model would do is it would instead take all of these embeddings, sum them together into a vector that kind of represents a sentence, and then take a weight matrix where the size of the weight matrix is equal to the size of the embeddings multiplied. So we have our embedding vector, I'll call it H, and we have a weight matrix, which is the number of columns is equal to the size of H. The number of rows is equal to the size of the number of scores we have. So actually, this should be wide and not long. And then this gives us a vector of scores. So the size of the vector of scores would be equal to 5, right? So then we take this, we add a bias also equal to the number of scores, to the size of the scores, and calculate scores, which we can then feed into the softmax. So, so what do our vectors represent now? So each vector has features, where each row in the vector is a feature. The features can correspond to anything we want. They could correspond to, is this an animate object? Is this a positive word? Is this something that tends to move, for example? We can then sum these features and use these to make predictions. However, there's still no combination features in this model. And the reason why is because we're still summing and multiplying. And if you do a little bit of math, basically you realize that if you took all of these red vectors and multiplied them by the weight matrix here, you would just get back the bag of words vector that you had in the previous model. So essentially, this is not any more powerful than the bag of words model that we had before. It's a different way of expressing it. It's not a more powerful model. But what it is useful for example, is like, let's say you have lots and lots of classes. Like, let's say you have 1,000 classes, and you only have a little bit of training data for each of the words. You might express the words as a 10-dimensional vector that then are used to make predictions over the 1,000 classes. And this would allow you to, for example, share statistical strength between predicting whether something's about whether a news article is about embezzlement or corporate corruption or something else. So then you could have one of the features be, like this is about a corporation, another one of the features being like this is about a crime, and then you could share strength among similar classes, for example. So this is not a widely used model, and the reason why it's not a widely used model is because it's not any more expressive than the bag of words model. But there is a model that is very similar that is actually surprisingly competitive in terms of being a classification model, or at least was, a couple of years ago. And the way this works is by taking all of these embeddings, summing them together, and then running them through a few nonlinear transformations, where each nonlinear transformation takes the hidden vector, multiplies it by a weight matrix, adds a bias, and then does some sort of nonlinearity on top of it. So something like a hyperbolic tangent. And the reason why this is good is now what we're doing, in a way, is we're not doing a single classification problem over, we're not doing like a single classification problem over whether this is good or bad, for example. Instead, we're doing a bunch of classification problems. So we're doing as many classification problems as there are purple circles in that vector. So if that vector, intermediate vector, has 1,000 different things, we can do 1,000 different classification problems. And these classification problems, and then we do this several times, we run it through, we extract features, we calculate the bias in the scores. So like classification problem number 1 could be something like, do I see feature 1 and feature 5? Do I see a positive word and a negation word? And if it's something like this, then you can say, I see a positive word and a negation word. Maybe that's a bad, that's a bad sign instead of a good sign. Then, equation number 2 could be like, maybe I see the name of a kung fu actor and something indicative that this is a romance movie. And if you see a kung fu actor in a romance movie, that's probably not a good sign that this is going to be a good movie. So, like you can come up with all kinds of different things that that could be indicative of the output. So yeah, not in hate, for example. So this is why neural networks are powerful. And I think if you've done a little bit of a neural network class or done a theory of a neural network class, actually you can maybe not exactly this model, but models that are slightly more complicated than this essentially will allow you to express any possible function that you would want to represent, and that includes doing perfect text classification for sentiment analysis. The only condition is that the neural network has to be large enough to capture all the features that you would need to be doing here. So I'll talk a little bit more about that next class. So are there any questions about this? Okay. Now I'll talk a little bit about definitions of neural networks. So what is a neural network? And from the point of view of this, this class, it's going to be something that's representable through something we call a computation graph. So the name neural network, originally the motivation came from neurons in the brain. I'm not a neuroscientist. I know a little bit about neurons in the brain, but nonetheless, I'm very good at training neural networks for natural language processing. So what this indicates is that actually what we're talking about now is something that is quite a bit different than the original motivation. And it's more of a mathematical object. It's probably more important that you are good at math, linear, like linear algebra differentiation, or programming languages to understand, modern parallel computing, high performance computing, to understand modern neural networks for NLP. But nonetheless, the basic idea is, neurons in the brain, they have a lot of synapses, and they get, like this neuron would be connected to the synapses outgoing from this neuron would be incoming to this neuron. And it's basically a function that takes in a lot of inputs, combines them together in some way, and generates an output. And that's similar to what we have the conception in computation graphs. So computation graphs are very closely connected to mathematical expressions. So mathematical expressions, I assume everybody in this room has taken math at some point in your life, or you got really, really lucky on the entrance exam. But an expression, can be anything, any sort of mathematical object like this. And let's say we have x, and we can take these expressions x and we can connect them to a graph. So we have x, which is a node in the graph, and a node is a value. And more accurately, it's an n-dimensional value, where n can be any arbitrary, positive integer. So the normal value would be, like a scalar. So we have 3.5. It could also be a vector. It could be a matrix, or it could be a tensor. So a tensor is something where it doesn't just extend in 2 dimensions, but it also extends in 3, 4, 5, whatever dimensions. In addition, we also have, we can extend the graph to represent a more complicated function. So like, let's say x is a vector, we can take the transpose of x. So that would reverse its dimensions. And an edge represents a function argument. So if we have the function, the node in this case represents a function application. And the edge represents a function argument. So a node with an incoming edge is a function of that edge's tail node. So if it's a unary operation, such as transpose, it will have a single incoming edge. If it's a binary operation, it will have 2 edges, and I'll give some examples here. So another very important thing with respect to deep learning or something, actually Jan LeCun posted his definition of what is deep learning online, and one of the important parts of that definition was gradient-based optimization. And what we mean by gradient-based optimization is essentially you need to be able to calculate gradients with respect to whatever parameters you want to optimize. And the way we do this in neural networks, in computation graphs, is we assume that every node we have, if it represents a function, we can also calculate the derivative of that function, or the gradient of that function, or at least the subgradient of that function. So with respect to this, we assume that we can calculate the gradient of the transpose. Functions can be nullary, so this would be an example of a nullary function. It has no inputs. They can be unary. They can be binary. So like, let's say we have something which is a matrix multiply function. You will have the matrix on the left, and you'll have the matrix on the right. Computation graphs are directed in a cyclic. It's written in Dynet. That's just, I forgot to update my slides. They're directed in acyclic in almost all modern neural network toolkits. And the reason for that will become apparent soon. But what this means is they don't have to be trees. You can reuse nodes like this. So here we have x transpose times a times x. Which means that we can reuse x again. So we can have this x going into multiple functions. Another thing is, if we want to, or if your neural network toolkit thinks this is important enough, it can also implement these functions in a more concise or efficient way. So like, let's say vector transpose times matrix times vector was a really common thing that you wanted to do a lot in whatever fancy neural network architecture you want to be using. You could either implement this through these kind of elementary operations with a larger computation graph, or you can implement it if your neural network toolkit implementer, or you yourself, if you like programming in C++ and can write GPU code or whatever, can implement a specialized operation that makes everything faster as well. So, for example, we could do something like this too. So then we can come up with something somewhat complicated like this. So this is a polynomial function. Maybe you'd want to implement the whole polynomial function in a single node, but this is a graph for this polynomial function. And then at the very end, we have a sum over all of the inputs. And then if we say y equals, this is a common thing we do in math, variable assignment. What variable assignment is essentially doing is it's just labeling the node in this graph with a name. So we have a lot of other nodes in this graph. These other nodes in the graph are still there. They just don't have a name. And the reason why they don't have a name is because when you calculated this function, you didn't think they were important enough to name. That being said, in neural networks, they still stay in your memory. So if you build a big graph, you build a big function like this, you will still have all of the intermediate results saved, unless you do something fancy, which we'll talk about later. So whether you do all of these in individual steps or in a single step, usually won't have any difference on the efficiency of the calculation. So any questions about this? Okay. There's some algorithms that go into calculating these neural networks. So the first algorithms, the most important ones, are graph construction and forward propagation. And what these do is they basically define the calculation that you want to do, and do forward propagation that actually calculates the values. So graph construction is basically constructing this graph. The way this normally works is you essentially write this equation in Python. You write this equation, y equals x transpose a x, whatever. For transpose, you might need to use like dot transpose parentheses, right? You won't write it exactly in math, but it'll be pretty close. And then behind the scenes, whatever neural network toolkit you're using is constructing this graph for you. And very often you can go in and inspect the graph, see what it looks like, etc. For forward propagation, what this means is essentially you start out with the values that you already know. So these are fundamental inputs to your graph. Maybe you got them from your data, or maybe they're parameters of your model. So these become initialized at the very beginning. They have no incoming edges, so they're ready to compute. And then we also have another couple nodes where each of these nodes is ready to compute because all of their inputs are also ready. They're also already computed. So now we just do a topological walk through the graph. And every time you update a node, you might or might not get a new node that's ready to compute. So now we have two other nodes that are ready to compute. We calculate that one, calculate that one, calculate that one. The order can be arbitrary as long as it's topological. And then at the very end, we get the output. And by the time we're done calculating the output, the values corresponding to these nodes will all be instantiated with the actual values. So if this is all you wanted to do, you wouldn't need a neural network toolkit. You could just do this in Python. You could do this in NumPy. You could do this in CuPy if you wanted to. If you wanted to do it on the GPU or something like this. However, what becomes very important is the gradient calculation, because this is what allows you to actually learn parameters. So what the gradient calculation does is it does backpropagation, where you process examples in reverse topological order and calculate the derivatives of the parameters with respect to the final value. So to give an example, you would start out here. You would, at the very end, your derivative usually is a scalar representing something called a loss function. It's something you want to minimize. The gradient with respect to that is 1. You want to reduce, and you calculate that. Then you take this 1 here, and you calculate the gradient with respect to all of the edges based on the gradient here. And then this gradient flows backwards into this node here. You update the gradient, then you calculate the gradient of this edge and this edge with respect to the gradient you got here. And you step gradually back through the computation graph in reverse order. So again, this is not something you have to implement yourself. This is what we have neural network toolkits for. But the important thing is that each of these gradient computations is not complicated. It's a relatively simple thing because each of the component functions is easy. And like we had in the example before, for each of the component functions, we can calculate this gradient exactly because we know math. However, by using this dynamic programming algorithm, we can calculate forward, we can calculate all the gradients backwards, and as a result, we can get the gradients of the parameters with respect, the loss function with respect to the parameters, and then we can update the parameters with respect to this gradient here. And we have alpha, which is a learning rate. It's maybe a value of 0.1 or something like this. And we take a step in the direction that reduces the loss function, changes the parameters to reduce the loss function. Are there any questions with respect to this? So as I said, we have lots of examples on the website of how to implement this. The next question is what neural network framework you should be using. There's a bunch of neural network frameworks, both historically and nowadays. The ones on the left here are frameworks that either originally or still are kind of static computation graph frameworks or static implementation frameworks. The ones on the right are dynamic implementation frameworks. And I suggest the ones on the right for reasons that I'll make clear. I should point out that MXNet and TensorFlow both have realized that this is an important thing and now have support for this. TensorFlow 2.0 now has eager execution by default. But what do I mean by the difference between these two? So the basic process in a dynamic neural network framework, and there's actually two different types of, there's maybe 3 distinctions that we have here. The first distinction is static versus dynamic. And the second distinction is eager versus lazy. And in dynamic neural network frameworks, the way it works is you first create a model, or you create parameters for the model, the things that you want to optimize. These might be, weight matrices, bias terms, tensors, whatever. Then for each example in your training data, or maybe each mini batch in your training data, you create a graph that represents the computation that you want. And you calculate the result of that computation. And if you're training, you perform back propagation and update. So what is the difference between this and a static neural network framework? The difference is in a static neural network framework, this create a graph thing comes before this for loop. So basically, you create the graph at the very beginning of training, and then for each example, you feed in data, you calculate the result of the computation, you perform back propagation and update, but the graph, underlying graph never changes. So this method is useful for image classification, for example, where all of your images have a size of, whatever, 256 by 256 or something like this. And the reason why is every single image you get will have exactly the same shape. You can use exactly the same computation over the image, et cetera. And because of this, what you can do is you can create the graph beforehand. You can then run an optimization process or something like this that really optimizes the graph to run as efficiently as possible. So like one example of a thing you can do is your program behind the scenes can recognize that you're using this form of something and say, hey, I recognize this, and I know an optimized operation that can do this faster, more memory efficient. So I will replace this by this at the beginning of training, and I'll save you a whole bunch of time in memory. So this is something, for example, that TensorFlow, if you don't use eager execution, you use, I think it's called session or whatever, will allow you to do something like that. However, the disadvantage is in NLP, for example, we might have sentences of different lengths. We might have documents of different lengths that have sentences of different lengths inside them. We might want to predict graphs. We might want to predict trees or something like this. And because of this, you don't have a single homogeneous computation for each example. And because of this, the power that dynamic frameworks give you is that you can create a different graph for each computation, modulo efficiency concerns. The other distinction is between eager versus lazy execution. So eager execution, basically what it does is every time you run an operation, it calculates the result of that operation. If you do eager execution, then you do A plus B, and immediately the system will start calculating A plus B. On the other hand, lazy execution basically creates the graph beforehand and then does the calculation afterwards. So even if you're creating the graph for every example, it will still only do a calculation afterwards. So the reason why lazy execution can be better in some cases is because this allows you to optimize the graph like I talked before. If you're doing eager execution, you don't have any space to do this. The reason why I mentioned this is PyTorch is a dynamic framework with eager execution. TensorFlow Eager is a dynamic with eager execution. TensorFlow Session is static with lazy execution. Dynet is dynamic with lazy execution. So Dynet is a framework that we made. It's sometimes good if you want to do things like tree-structured neural networks or graph-structured neural networks that you would like to be able to both optimize and use dynamic structure. But we can talk about that later. But these are kind of interesting things to know with respect to frameworks and how they affect NLP. So as I said, we have some concrete examples of how to implement both of these in PyTorch and in Dynet, so you can take a look at those. So are there any questions about this? Yes.
So I had a question about the logistics.
Yes.
So will the recordings be posted on?
Yes, the recordings will be posted online. On YouTube, usually a day or so afterwards. I'll try to put a link, but sometimes I forget to put a link on the class site. So at the very beginning, I'll give you a link to the YouTube channel, so you can just follow. Yep. Any other questions? Yes.
What is the advantage of eager versus lazy?
Okay, so why would you use eager instead of lazy execution? There's two advantages. The first advantage is that it's a little bit simpler, perhaps. I don't know if that's even an advantage. For you, it's maybe more of an advantage for the implementer of the system. The other advantage is if you're implementing in a language like Python, which is relatively slow, it's quite possible that the actual graph construction can be slower than executing the neural network itself. And in those cases, it would be better to start executing while you're still constructing the graph, so you can do both of them synchronously. And if you're calculating on a GPU, for example, you can dispatch an instruction to the GPU and then continue building the graph in Python. So there is definitely an advantage with respect to that. That's a good question. Any other questions? Okay. So I have a few things to remember going forward. So the first thing to remember is neural networks are very powerful. Hopefully you knew that, and that's why you want to take this class. In fact, they're universal function approximators and can calculate any continuous function. So what you should know is if somebody tells you a neural network cannot do that, they're lying. A neural network theoretically can do that. It can solve any of the problems that we want to solve in computer science. It's a Turing machine if you formulate a neural network appropriately. So a neural network can solve your problem theoretically. But language is difficult. There's lots of corner cases and things like this. And most importantly, data is limited, and our optimization algorithms cannot necessarily find the solution that you want to find. And because of this, to solve any realistic problem, even the really, really big data ones, you need to have an appropriate design and appropriate optimization algorithm that allows you to do this. So anytime I talk here, there's always going to be a trade-off between how much data can you get to solve your problem and how much do you need to work on getting the details right. And just to give, I was just looking on Google Translate between English and Japanese, and this is one of the best data scenarios we could possibly have. I don't know if there's 10 billion, but there's certainly over 1 billion parallel sentences between English and Japanese, and still, Google Translate fails, quite badly at translations that a human translator could get very easily. Choosing the right word sense, for example. So, there's still lots of work to be done here, but it's very exciting times, and things are working a lot better than they do now because of the tools that I hope to teach in this class. So in terms of the class plan, I'm just going to go through this very quickly. It's on the website. But we're going to start out talking about models of sentences and sequences, including bag of words, bag of n-grams, convnets. We're going to talk about recurrent neural networks and variations of them. Near the end of the class, we're going to talk about modeling documents and longer texts. So when you want to move beyond sentences into like documents or dialogues or something like this. We're also going to be talking about implementing, debugging, and interpreting. So I think this is really important if you actually want to build systems. A lot of your time is going to be spent learning how to make things finish in time for you to turn in your assignment on time and fit on one GPU because, fit on one GPU or how to do parallel training so you don't have to fit all your data on one GPU or something like this. So these are really important things if you want to build anything practical. Also, when things go wrong, how do you know what is going wrong and why? Because neural networks are harder to interpret than simpler models very often. Then we're going to talk about condition generation. So this is basically like encoder-decoder models, attention, self-attention, transformers. Pre-trained embedding. So one of the big things of 2019 was a huge success in taking lots of textual data and feeding it into unsupervised feature learning algorithms, for things like BERT or Roberta or XLNet or Electra is the new one that everybody needs to know now, apparently. So, we're going to talk about pre-training. Unfortunately, all of these things have fancy names that conflate a lot of different things together. So we're going to talk about it in a systematic way, like what is your model, what is your data, what is your training objective, and try to detangle these to bring a little bit of sense to the chaos in the field. Also structured prediction models. So how do we predict things with complex structure? How do we train models so that they're effective at predicting things with complex structure? So, sequence prediction, tree graph prediction, maybe better training algorithms for text generation, for example. Trees and graphs is the next thing. Also advanced learning techniques. So models with latent random variables, so things like variational autoencoders or topic models. Adversarial networks and semi-supervised and unsupervised learning methods. Also, QA is something that is very interesting nowadays. There's a couple ways to do QA. One way is to do QA over structured databases. So you have a big database of all the people in the world and where they were born. And then you ask, who are all the CMU professors who were born in Pennsylvania? Or something like that. And we'll give you ways to solve that problem accurately and not answer like Hillary Clinton or something like that. Machine reading in text-based QA is where you have text. You want to read the text, extract information from it, and answer questions about that information. And finally, multitask and multilingual learning. So how can we apply these methods to learn over different tasks and maybe learn over different languages. And one final thing is something we were working on new for this class. We've restructured this class just a little bit. Specifically what we did this time was we came up with a repository of concepts in neural networks for NLP. This is also linked from the class site. And what I wanted to do basically was say, if you pay attention in this class, you should be able to understand the major concepts in 90% of papers in state-of-the-art NLP venues. And so we decided to take an empirical approach where basically I created a list of concepts here. And there's the names of all of these concepts, and I'll try to go through all of them in detail throughout the class. And we also did some manual annotation of papers to say this paper is using this concept, and also automatic annotation here. So the most important concept in papers in NLP is attention, apparently, which is something not surprising if you know what attention is, but if you don't know what attention is, it's something you really need to know. And then there's also things that are a little bit less, either they're used and not mentioned in the paper, or they're just not used as much. But I think one of the good things is the more minor concepts are the things that maybe aren't quite as explored yet. So they're good concepts for you to know, with respect to coming up with new ideas. And then if you come up with a new idea that I want to use meta learning for named entity recognition, you could then browse the list of meta learning papers. If you don't know what meta learning is, don't worry. We'll probably talk about that as well. And you could go click on this link, and Pengfei has created a thing where you can browse all the papers that our classifier guest used these concepts. So this was kind of a new thing that we're trying this year, and hopefully it'll be useful. We'll see. If it doesn't work, I'll forget it next year and just do the same thing we did before. So, okay. Yeah, that's all I have for today. Are there any questions? Yeah.
I saw you mention inductive bias just now. Can you elaborate a little?
Okay. Yeah. So what is inductive bias? That's a good question. So inductive bias is basically some sort of structure of your model or training algorithm that makes it learn what you want it to learn.
Right.
So it's a very vague concept, but it's basically trying hard to make your model learn the way you want it to.
But is it good or a good thing or a bad thing?
It's a good thing if you give it the correct inductive bias that improves accuracy. Yeah. Okay. Any other questions? Looks like everyone's ready to go, so I guess not. I'll be up here for a few minutes afterwards. So, see everyone on Thursday. Oh, please look at the website. There's reading material for Thursday on the website. Please read that and come here because there will be a quiz on the material. That's all. Thanks.
Are there any quizzes?